Dear students, today I will discuss about forces due to magnetic fields. There are three different forces. The first one is force on a charged particle, and second one is force on a current element, and third one is force between two current elements. So I will try to complete all these three topics today. Let us see the first one now, that is force on a charged particle. First one, force on a charged particle due to magnetic field. If it is placed in the magnetic field, some force will be exerted on this particle. We will see the direction of it, that force also. Force on a charged particle. This charged particle can be plus q or minus q. That is positive or negative charge. This is a charged particle. Charged particle, and let u be its velocity. Let u be its velocity with which it is moving. Velocity. It can be stationary or it can be moving. If it moves, its velocity is u, meters per second. Meters per second. Let us consider the movement of the charged particle in the electric field separately, magnetic field separately, and influence of both the fields on this magnetic field. We will see all these things. Let us consider an electric field. Electric field denoted by E bar, and I am placing the charge Q in this electric field. It is stationary. Okay. Now, what is the force on this? Let it be Fe, be the force on this charge, which is equal to Q into E. That this one already covered in the earlier classes. That is, force on Q due to this electric field is Q into E. Even it is moving also, even it is moving with velocity u, also same force will be exerted on that positive charge particle. It can be plus q or minus. If it is minus q, the force will be in this direction. If it is plus q, force will be in this direction. Okay. Since it is moving in the direction of charged particle, it performs some work on that. So, if it is placed in the electric field, the force exerted by this electric field will perform some work on it. So, it performs some work. Performs some work on this charged particle. Since this force is acting in the direction of the particle, and if it is stationary or moving, the same force will be acting on that. If it is stationary, stationary, what will happen when the force is applied? It starts moving. If it is stationary, that is, if Q is stationary, it starts moving. It starts moving. Okay. If it is moving, it means Q here. If it is moving with velocity u, initial velocity u, due to application of this force F, the velocity will be increased. That means it will be accelerated. So the velocity will be increased. Velocity will be increased. That is, due to application of this force, the kinetic energy will be increased. Kinetic energy of the particle will be increased. That is, kinetic energy of the particle will be increased. Okay, let us consider magnetic field. Magnetic field. This magnetic field is towards right direction. Now let us place the charge Q now in this magnetic field. It is stationary now. When it is stationary, no effect on this. There is no effect. There is no effect on this charge. Okay, if it is moving with velocity u, if it is moving with velocity u, then a force will be exerted on that. If it is moving with velocity u, a force will be exerted on that. That force due to magnetic field is equal to q into u cross b. So what is the direction of the force? By applying the right hand palm rule, we can find out the direction of the force. The magnetic field is this side. Therefore, let us suppose if it is moving, q is moving in this direction, velocity u. The magnetic field direction is shown by these four fingers. Thumb shows the direction of the charge, that the movement of the charge. Charge is moving upward, and my direction of magnetic field is shown by these four lines. So this palm shows the direction of the force. Force will be inside the board. That is shown by the into. Force will be inside. Okay. So that force is magnetic force, which is equal to Q into U cross B, newtons. Newtons. Here also it is newtons. Newtons. So let us consider both electric and magnetic field now. So this is electric field. Magnetic field, let us say it is going into the board. So shown by this into symbol. This is the magnetic field. And let us say the Q is moving in this direction with velocity U. Now let us apply this right hand palm rule and find out the direction of force now, which is exerted on this Q by magnetic field as well as electric field. That force is equal, total force is equal to, due to electric field is Q into E, plus due to magnetic field, this is called as Fe, and due to magnetic field is Q into U cross B. Q into U cross B. This is due to magnetic field. This is the total force on this. What is the direction of force? The magnetic field is, with respect to magnetic field only, we can find out the direction of the force. It is into the board, and thumb showing the direction of the movement of the charge. So it will be towards left side. The force on this will be towards left side due to magnetic field. And Fe is towards right side. Generally, the magnetic field will be, this Fm is much less than the quantity of the value of this Fm, that is the force due to magnetic field is much less than force due to electric field. So we should remember this formula. This is the total force on the charged particle due to electric field and as well as magnetic field. This force due to electric field will be in the direction of the charge, and force due to magnetic field will be at 90 degrees to the direction of the charge. According to Newton's second law, Newton's second law, F is equal to ma. F is equal to ma, which is equal to m into du by dt, rate of change of velocity, which is equal to q into e bar plus u cross b bar. Equation is used for determining the motion of the charged particle Q. Okay, next we'll move on to this Second one, force on a current element. Force on a current element. For the first point, that for the first one, force on a charged particle, just remember this equation. Okay, what is the force on the charged particle in electric field? What is the force on the charged particle in a magnetic field? And add those two, and it will be equal to total force. Okay, I also tell you the direction of the force also. Second one is force on a current element. Force on a current element. Force on a current element. Okay, to determine the force on a current element of a current carrying conductor, we should recollect IDL is equal to KDS is equal to JDV. We should recollect that equation. And right here, to determine the force on a current element, the force on a current element, to determine the force on a current element, IDL, this is the current element of a current carrying conductor due to the magnetic field, due to the magnetic field. We should recall the relationship. We should recall the relationship between the current elements, between the current elements. Actually, what is current element? For example, if current is flowing through this conductor, let I be the current is flowing through this conductor. Let L be the length of the conductor. We will consider a differential length DL. Consider a differential length DL. Let this be DL, and current in that into DL. Current will be same current will flowing through this differential element, and through the conductor same current will flowing. This current element I is called as IDL. DL is the differential small length of the conductor. IDL is the current element. We are calling that as current element. This is current and this is differential length. We call the product of these two is called as current element. Okay, we should recall the equation, that is IDL is equal to KDS is equal to JDV. Okay, this is line current, this is surface current, and this is volume current. That is I is called as line current, and K is surface current, and J is volume current. The line current need not explain. What is surface current? Let us consider surface. Let this be surface. So, through the surface, current I will be flowing. Let this be I. Okay, and let this be some distance D. Let us say. So, current by this distance is nothing but K. That is K is measured in amperes per meter. So K is the surface current which is measured in amperes per meter. Okay, this total current divided by the length of the surface. Length of the surface. Okay, we'll get K. For finding K, I will be the current flowing through the surface and the width of the surface be D, then K, that I by D is nothing but K. K is the surface current. And for volume current, let us consider a cable. Let this be cable and let this be current density J. Let I be the current. So what is the current flowing through the cross section of this cable? That is I by A. I by A. So J is equal to I by A, that is amperes per meter square. This is the volume current we can say. So if you can equate all these three, IDL is equal to KDS is equal to JDS. All the units are ampere meter only. Units will be ampere meter only. Okay. So you can check that ampere meter, length is measured in meters. KDS, what are the units of this? KDS is ampere per meter into meter square. Again it is coming to ampere meter. Here it is ampere per meter square into meter cube, ampere meter. Okay, you should recollect this expression or equation. Ideal is equal to KD is equal to JDV. What we are going to find? Force on a current element. Force on a current element due to magnetic field only. Okay, so F is equal to force on this current element is equal to Q into U into B. This is the formula just now we have seen. F is equal to Q into U into B. So what is DF? DF is equal to DQ U bar cross B bar. Okay. And ideal, let us find out from ideal. Ideal is equal to what is definition of current? Current definition of current is rate of flow of charge. That is dq by dt. dq by dt. I am writing a dl by dt. I am instead of writing dq by dt, dq dl by dt I am writing. So what is dl by dt? dl by dt is nothing but u. That is velocity of the charge. So ideal is equal to dq into u. So this df is equal to in place of this you can write ideal. Ideal cross B. Ideal cross B. So integrating on both sides we will get F is equal to integral. F is equal to integral. For this line current it is for the closed loop indicated by the circle. Okay. For this line current ideal we can write here as IDL cross B. This is the force due to magnetic field. Whenever the charge is placed in that magnetic field, the force exerted on that is integral IDL cross B. That is, whenever this current element is placed in the magnetic field, not charge. Current element is rate of flow of charge dq by dt. Okay, so IDL is the current element. If it is placed in the magnetic field, the force exerted on this current element is IDL cross B, integral of that. And what is ideal? It is equal to KDS and also it is equal to JDV. So it can be written as integral. Now we use surface integral. Yes, surface integral is of ideal, right? KDS. DS is also a vector cross B. Cross B. And this is equal to volume integral. Volume integral JDV cross B. Okay. This is all about force on a current element. We can also define this magnetic field from this current element. From this current, where is this current element? Current element. This is the current element. So we can define this magnetic field as, that is, DF is equal to IDL cross B. Okay, from this we can define the magnetic field as it is defined as the force per unit current element. So B is equal to dF by IDL. So dF by IDL can be, we can define like this. B, that is magnetic field, is equal to force per unit current element. In that way also we can define magnetic field. Let us see about force between two current elements. Force between two current elements. Third one, force between two current elements. Current elements. Current element is nothing but ideal only. So I will take two loops, loop currents. Okay, let us take a battery which supplies current. Let this be loop. Okay, let this be battery supplying current I1. So here let this be IDL, I1 DL1, I1 DL1, and another loop. So this is the current be I2, and here it is. This is I2 DL2. This is the second current element. This is the first one. First one. This is second one. Two loops I have used. There is the two loop currents. This is the battery. The current direction is, this is anti-clockwise direction. This is clockwise direction. Let us find out the force between two current elements. So this is the loop current. This is another loop current. In this is the current element. This is the current element. Current element IDL1. Here I2 DL2. Here it is I1 DL1. By Bayes what law? This I1 DL1 will produce a magnetic field at this point. Let us say the current is flowing like this. So the curled fingers, current is moving up in the conductor. Let us say this chuck is a conductor. The magnetic field will be entering here. Let this is magnetic field. Let it be B1. B1 is into the board. Due to I2 DL2, the magnetic field here it will be leaving the board. It is the B2. So curled finger will come out. Here enter, it's comes out. So take here, curled finger shows coming out. So that circle dot shows the direction of the magnetic field coming out of the board B2. Let us find out the force on this ideal one due to magnetic field because of this I2 DL2. So because of this B2, what is the force on this? Let us find out, and let the distance between these two elements be from here to here. This is vector R12, and from here to here, if you consider this, it is R21. R12 is equal to R21. And let Q1 be charge in the moving charge in the loop 1, and U1 be velocity of Q1. Q1 is velocity of Q1, and here what is the magnetic field? B2 is the magnetic field due to I2 DL2. Because of this, magnetic field B2 is produced. What is F1? What is F1? Let the force on this be F1, and let the force on this be F2. F1 due to magnetic field produced by I2 DL2. Okay, that is F1, force F1. What is F1? F1 is equal to Q1 U1 cross B2. Why? Because the magnetic field here is B2. What is the direction of this force F1? This palm direction is like this, and what is the velocity direction? So we can show like this. The ideal one direction, that is Q1 direction is upward, and magnetic field is like this. The palm direction is towards this right side. So force F1 will be in this direction. F1 will be in the same way F2. Here F2, the palm enters into the board and the direction is shown by thumb. So this palm will be in this direction. So F2 will be in this direction. F2 will be in this direction. So what is F1? Q1 into U1 into U1 cross B2. These two are vectors. Okay? Two are vectors. I1 dL1 is equal to dq1 by dt into dl1 by dt. Instead of writing here, I am writing here, which is equal to dq1 u1. So I1 dl1 is equal to dq1 u1. So here what is df1? df1 with respect to u, we differentiate. With respect to q, we differentiate dq1 u1 cross b2. df1 is equal to dq1 u1 is I1 dl1. I1 dl1. So if we again differentiate this with respect to b, then we will get dq1. Instead of dq1 u1, I can write I1 dl1, I1 dl1 cross b2, differentiate with respect to b, so I am writing here b2, db2. Now let us apply Biot-Savart law. Biot-Savart law. What is Biot-Savart law? The magnetic field intensity due to current element at the given point is directly proportional to IDL and also sin theta, and inversely proportional to the distance between the IDL and that point. Okay, so that is H1 is equal to 1 by 4 pi is the constant into IDL cross AR cap by R square. This is the derivation we have seen in the Biot-Savart law. But here we need dB2. So dB2 is equal to mu 0 by 4 pi. Mu 0 h is nothing but B is equal to mu 0 h in free space. I am using this equation here. So dB2 is equal to mu 0 into 1 by 4 pi into I1 dL1, not I1 dL1. Because of this IDL2, I am finding dB2 here. I2 dL2, I2 dL2, I2 dL2 cross A. What is the unit vector now in this direction from this loop to this one, R21. So it is AR21 cap. The unit vector in the direction of R21 by R21 square, This is the magnetic field produced by this I2 dL2 at this point. That is differential magnetic field I am considering. Okay. Now let us substitute this in this equation. Okay. Wherever dB2 is there, let us place this expression. So D of dF1 is equal to I1 dL1 cross, what is dB2? That is mu 0 by 4 pi I2 dL2 cross A21 or AR21 cap, the unit vector in the direction of R21 by R21 square. So this can be written as I1, I2 and mu 0. I'll take out mu 0, I1, I2 by 4 pi dl1 cross dl2 cross a r21 cap, r21 cap by r21 square. This is d of df1. If integrate twice, we'll get f1 is equal to integral L1, L2. That is a closed path L1, L2. You will get mu 0 outside. F1 is equal to mu 0 I1, mu 0 I1, I2 by 4 pi dl1 cross dl2 cross AR21 cap by R21 square. Okay, this is F1. This is F1. Measured in newtons. F1. Let us find out F2 now. F2, we can get F2 by interchanging the suffixes. That is 1 to 2 and 2 to 1. DL1, the suffix is 1. We will make it 2. Then we will get minus of F1 will be equal to minus of F2 and F2 will be equal to minus of F1. Why? Because Newton's third law applies here. Okay? Action is equal to reaction. F1 will be equal to minus F2. So F2 is equal to, just interchange the suffixes, mu 0 I1 I2 by 4 pi integral L1 L2, close integral L1 L2 dl1, I am writing dl2 cross dl2 as dl1 cross AR21 is equal to AR12 cap by AR12 square, because AR12 is equal to AR21, in vector is also same here, so no need to modify this. This will be same. R12 is equal to R21. Only thing is this cross product. So F2 is equal to mu 0 I1 I2 by 4 pi integral L1 L2 integral, not L1 L, integral L1 L2. This dl2 cross dl1 is equal to minus dl1 cross dl2. That is A cross B. A cross B is equal to minus B cross A. So let us apply that here. So it will be equal to minus dl1 cross dl2 cross A R12 cap by A R12 square. So F2 or F1 is equal to minus F2. F1 is equal to minus F2. So with this, the last but one topic in the second unit is over. So viewers, if you think that you have understood this lesson well, this video lesson well, please like, share and subscribe. Thank you.